Kind of the first thing to consider or think about when you're looking at upgrading your factory brake system is what the brakes are doing. And what the brakes are doing is converting energy of speed into heat. So thermal management is kind of the biggest key of what the brake system is doing. Right, so on a street brake system that Porsche has developed, you have all of the characteristics that they want with high stopping power, excellent feel, excellent feedback, and the thing to consider of why you need to upgrade for any higher performance or track day type events is because of the thermal management. Not so much because of the mechanical stopping power, but the ability to shed heat and not damage any components on the car. So the major differences between a street setup and a track or racing brake system comes down to the components themselves. Street system is really emphasizing low noise, low dust, durability, versus a racing system is emphasizing consistency at elevated temperatures and the ability to shed off temperature that comes with much higher speeds than you'll normally see on an everyday street car. With brake rotors themselves, you have a variety from slotted, drilled, plain smooth finish rotors, one-piece cast iron, two-piece where you have cast iron friction rings and aluminum brake hats, to even the carbon ceramic lightweight assemblies. So advantage of a cast iron is it's inexpensive to produce, and also cast iron produces a very good braking friction surface to interact with the brake pads. Its disadvantages are its weight, and because it's one piece connected directly to the hub, as you get high heat into that system, it can distort and move around in ways that don't keep it running as smooth, which can lead to pedal feedback issues, pulsing pedals, other things like that. So that's where you step into a two-piece system where the friction ring of the braking portion is disconnected from the aluminum or steel hat hub section. This allows it to run better as you increase your temperature. So the difference between a cross-drilled and slotted rotor or even smooth finish rotor, a lot of it has to do with technology of when braking systems first started becoming important for a disc brake system in automobiles with racing. Pad compounds and formulations at the time would outgas and produce a lot of gases during these high heat moments that could lead to some poor braking performance. So the brake disc was cross-drilled to allow those gases to escape. Slotted rotor really is adding a little bit of better friction, better characteristics for racing brake performance. A smooth rotor is really ideal for low noise and low wear. So with a slotted rotor, and why it can increase pad wear a little bit, is because it does produce kind of a cleaning action, like a cheese grater against the brake pad, to slice off kind of the hardened material that can glaze over sometimes during different braking events. Lower speed stops that don't generate a lot of heat can kind of glaze up the pad surfaces. So you want to have that fresh braking surface against the iron rotor. So pad selection for different types of driving, racing, sporty performance, there are a wide range. So the brake pad generates friction against the iron rotor, and how stable it is throughout the temperature range will determine its characteristics of what it's good for. There's also characteristics such as noise and brake dust that are a concern as well. Each pad can be formulated to do specific things better than another. Some pads can be more all around. For a street pad, for example, you really want good friction and good stopping power throughout the temperature range your vehicle could be operated. Whether you're driving in the winter or a hot summer, you want to have good stopping power. Also with weather conditions, rain or snow or any of that, you want to make sure that you have a good stable pad. Where a street pad can fall off a little is because of the characteristics of noise, low dust, and low temperature friction. It can't always handle high temperature. So sporty driving, performance racing, these all generate a lot more temperature. So the brake pad compounds themselves and formulations will start to lose braking power as you increase temperature. And that's where a race compound comes into play, where it's both much harder than a street compound and has higher friction characteristics. Some can be tailored to where they also increase much with temperature rise. So you can really fine tune it for exactly what application you need. So really in terms of pad grades of different types of pads, what it comes down to is the temperature range you're operating in, and also sometimes the vehicle type. You can design a brake pad to increase friction with temperature. You can design a brake pad to be very stable at temperature, so it maintains the same braking performance no matter what temperature it's at. Or you can actually design them to have a slight drop in friction at temperature. And a lot of it suits the exact vehicle specifications of what you're doing. In racing, it could be, say, an autocross event where you don't ever get out of second gear. You're not generating a lot of braking heat, but you still need a very high biting pad initially at cold temperatures. You don't really care about the elevated temperature performance as much as, say, an endurance race car that is seeing high speed stopping and braking zones where you're generating a massive amount of energy, or high downforce cars that they have a lot of downforce at higher speeds, so they can use more braking power at those higher speeds, but as they slow down, you actually lose braking performance because you're losing downforce. So you actually, in some cases, need a pad that can back off on its own. So each different, even racing scenario, street scenario, performance driving, there are little small things you can do in the brake pads to give you kind of the best you can have for that application. So yeah, a race or track day pad on a street car, the biggest thing you have to worry about really, if it's a concern, is that it may not have much friction at a cold temperature. Depending on the environment, it may not be something you notice much. A lot of people can just push a little harder on the brake pedal. Like you, I have race pads on my street car. They make a little bit of noise at low pressure where they squeal and squeak a little bit. And I do notice, compared to a street pad, when it's colder outside or early in the morning when I first go to drive the car, that first brake apply, if it catches you off guard, you have to realize, oh, I got to put a little more pedal effort into this because the car isn't braking as slow as I expected, because that race pad hasn't come up to temperature. And if you were to do that stop, say 3 or 4 times pretty hard, all of a sudden that race pad would start to come on temperature and you'd start to get really good braking performance out of it. So definitely not something recommended for everybody. If you know what you're dealing with, you know it's okay, I have to apply more brake pedal pressure, but also it is a scenario where it's something where you may not have the stopping power, ever have the temperature that pad was designed for. And really, the brake pad and the brake disc is the core of the braking system. And the brake caliper is essentially just a tool that allows the pads and the rotors to work, to generate heat, to absorb the mechanical energy that's been generated by driving fast. And sometimes we drive very fast. But the caliper's biggest role is to provide a stable platform for the brake pads to be able to apply equal pressure even pressure across the brake disc so that the heat generated gets generated in a very, what would be the word, kind of like not a precise but a consistent manner where it's consistent across the brake face of the cast iron discs, and that's its biggest job. Yes, it does provide the clamp load for the brake pads that allow them to counteract against the brake rotor, but its biggest role is being a stable platform for the brake pads. Calipers over the years have evolved from a single piston to multi-pistons where 4, 6, 8, the new Taycan Panameras, it's a 10-piston caliper. I know there are other companies that have done 12-piston calipers. And even to that regard, if you push braking systems up to an airplane, they have multi-piston calipers that cover the entire circumference of the disc. So it's like, well, why have more pistons? And what it comes down to is the clamp load is something the engineers and designers from the factory have a specified range. They want the brake system to provide X amount of torque. So what they're doing hydraulically is it can be a single piston or it could be a dozen pistons. If sized correctly, it provides the same clamp load. So the multi-piston really comes about when you have a change in brake pad dimensions. When the brake pad goes from being a small little square or puck that you would see on smaller race cars or earlier cars to being a very large object. For example, I think the new Panameras now, I think that brake pad we've seen them, they're about as big as bus and truck pads that we see on commercial application vehicles. And so the question is, well, why do you need such a big brake pad? And it is because of heat and wear characteristics. So by making the brake pad overall dimensionally bigger, you can absorb more heat energy without having to go to a really wide brake pad. So with all the design of the suspension, the brakes, the wheels, the packaging, there's a lot of little things that the engineers and designers have to look at when putting it all together. So if they say, hey, we need more heat energy or more absorption of the heat energy, we can't go wider because the caliper would then hit the wheel. So what we can do is make the brake pads taller, or we can make the brake pads longer. But if you stayed with just a single piston, you put a single piston in the middle of that very large brake pad, you get really good pressure at the middle of the pad, but on the edges, it doesn't have very good pressure against the rotor. And that's what's generating your stopping power and your friction. So if you just bend the brake pad, you don't generate a very good braking system. So by spreading pistons out around that brake pad, by going to multiple pistons, you can spread the pressure out around that pad to have a much better braking surface. So yeah, in terms of a Panamera, 6,000 pounds, that's also capable of doing 200 miles an hour, or pretty close to it. And that's why, like I made the reference to a commercial duty bus or truck. Yeah, while they can't go 200 miles an hour, they have weight on their side to where they may be 20,000 pounds. So it means that stopping power, whether you're generating it from a 200 mile an hour stop down to 50 miles an hour with a 6,000 pound vehicle, you need to be able to dissipate X amount of heat. And that it kind of is a standard. Whether you have more speed or higher weight, you've got to be able to dissipate heat. And that, like I was talking at the beginning, heat rejection, heat dissipation is the purpose of the brake system ultimately. And that's the key driver of many of the components of what goes into street versus race versus track day, is that ability to reject heat and dissipate it safely. Yeah, brake fluid is pretty key. Now, little asterisk, it is maybe one of the worst things in the world. It's the biggest thing I dislike about brake systems is brake fluid. But it is so very important because it's the means of the hydraulic system to allow that clamp load to happen. So getting back to the heat generated in a braking system, why is that important for the brake fluid? Well, the brake fluid sits inside the caliper very close to that heat source. So as a caliper, if you have a lot of temperature go into the brake caliper, that temperature transfers then into the brake fluid. Brake fluids, as they heat up, if they don't have special characteristics in them, when you go to apply the brake pedal, it's gotten enough heat in it that it has boiled off and generating air pockets inside its fluid. And when you go to push on the pedal, air compresses and you have no braking power. And that can happen as fluid ages. The other thing that happens with brake fluid is it's actually hydroscopic, which means it absorbs water. And while we think our brake systems are sealed and nothing can get out, it can absorb moisture from the atmosphere. So when you see that recommendation that change the brake fluid before any track day event, or in a factory service manual that says, hey, change the brake fluid after 100,000 miles or 4 years, it's because they're expecting a certain amount of brake fluid to have absorbed water. And water, like air in the system, as you add more water into the system, it compresses. It also reduces the brake fluid's ability to stay firm and rigid at elevated temperatures. So a brake fluid flush, even though it looks perfectly fine, could bring a whole new life back to your brake system where you have a much firmer pedal response is better. So especially for a weekend track event or a driver education event, is like doing a fluid flush with nice new fluid is a key to having a properly working brake system. So with brake fluid, obviously there's performance aspects, but there's also cleaning agents in the brake fluid. Like any system, the engineers from the factory, everyone's designed it to be able to keep all of the environment elements out, road grime, grit, dust. I mean, brakes themselves producing a lot of brake dust, a lot of iron materials, a lot of the pad materials are coming off in very fine forms. So as much as you can do as a designer to do a dust boot or to add protection for the brake fluid, some of that can get contaminated. So also changing your brake fluid is about flushing out old fluid and old contaminations, and also putting fresh new fluid in, refreshing seals. It also gives you a good chance to take a look at the sealing characteristics and say, hey, are my dust boots torn? Are they allowing dust and other things to get into the hydraulic system, which can cause problems, cause leakage, and poor performance out of the brake fluid? A note about the caliper and the dust performance is directly tied into the track performance as well. So with track performance brake systems, and one reason to upgrade a caliper is because, again, heat will kill a lot of the things put in place by the factory to protect the hydraulic system from contamination. So talking about caliper performance, dust boots, seals, they're all crucial to the brake caliper performance. If those experience a lot of heat, they can tear, they can burn, and that's something we see very common, where an excellent brake system on a street car, if you do some heavy track braking, track events, you'll see your caliper could start to discolor on its paint, the dust boots get hard and start cracking. So it's ultimately that it doesn't have the heat protection for the performance driving that comes along with a dedicated like track event or hard braking. It's a lot of heat being generated, and it's something that's why we recommend a full upgrade if you're doing that, or why race cars have a completely different brake system designed specifically to handle that kind of heat and be able to have seals or no dust boots, or a system that is a little bit higher performing, but they also know, okay, without a dust boot, I have to clean and prep this better. You know, a race car prep is a little more involved than a street car prep, where you're going through the car to make sure that everything is in working order much more often. Similar to the engine performance, the race car, after a 24-hour race, it has to be rebuilt. Race car brakes, while they don't have to be rebuilt after 24 hours, they take more attention than street car brakes. A street car brake system is something that's very capable of doing high performance, but ultimately it can't take the heat that's generated in a true racing scenario. All right, so discussion about the different material types of a brake rotor. We have, your cast iron, you have your carbon ceramic. Porsche has their new tungsten ceramic coated brakes. That's an iron disc with a special coating on it. It's like, well, why have all these different types of brake systems? Part of it comes down to performance. Part of it comes down to costing. Like a cast iron brake disc has very excellent friction characteristics with the standard metallic ceramic type brake pads, but it is heavier. It has temperature limits as well. You can't go too high on temperature without it wanting to break apart, crack. Cracking is a big reason why a cross-drilled rotor is not great with an iron disc. Anytime you put a drill hole through that, as it heats up in heavy-duty braking applications, it wants to crack around that hole. So it can lead to cracking early by having a cross-drilled iron rotor. Slots, they help frictional characteristics. The tungsten carbide coated that Porsche has done with the new vehicles adds a very hard ceramic or tungsten carbide type coating onto the iron brake surface. And that was done for, I imagine, a couple reasons, but the biggest one it gives you is very low brake wear on the iron. So what a lot of people don't realize is that most of the brake dust that happens is coming from the iron brake disc wearing off and not so much the pad material. Through the life of a pad, you will see so much more wear coming off the iron rotor. It just doesn't seem like it because it's a few microns, 100 microns, 0.1 millimeters. It's not very much compared to what you see on the brake pad, but because it's the full circumference of the disc, there's so much more material. So to highlight a low wearing disc, they also painted the calipers white. So you see that it has very little brake dust because of very hard tungsten carbide coating on there. The ceramics take that to another level where also, like the tungsten carbide coated, they have very low wear, almost no wear at all because the brake surface is very, very hard. Now, one downside to this is that it's a lot harder to generate good friction with a very hard surface with a brake pad. So it takes another specialty brake pad to be formulated to work with that very hard surface. But the benefit of the ceramics is that they have very little wear, and when properly taken care of, they will essentially last the life of the vehicle. And they also have very, very low weight. So the low weight is really awesome for performance. And it also means that you can increase the size of the brake disc without the weight penalties of a very large iron disc. So carbon ceramic is very, very good. Ceramics and carbon in general, they don't expand much with temperature, which is really awesome for durability and high performance driving. The ceramics, because it is a ceramic, can be a little more brittle. It's why you have to take big care when changing them out or doing anything with them. The next step up from there that racing vehicles use is a pure carbon disc that is a specially formulated carbon fiber brake disc that goes through many special operations that take 6 to 8 months long to produce a brake disc, whether it's 1 or 100. It takes 6 to 8 months to produce. But what that gives you is a carbon fiber brake system that's able to handle heat and temperature, but also isn't as susceptible to the brittleness of ceramic. But the downside to that is it has very little friction at lower temperatures. So unlike a racing brake pad on iron that you can get away with it on the street, on a carbon brake system, you have almost no frictional characteristics at low temperature, so you're not going to stop the vehicle. You'd be surprised at how little performance it has. But that's also why in racing you'll see them warming up their brakes and doing some brake applies, or being cautious on that first corner when they know they have cold brakes, because until they get a substantial amount of heat, and we're talking 400 to 500 degrees Celsius into the brake discs, they're not going to generate the frictional characteristics they're looking for that give them the stopping power. So carbon ceramic is a great option for the street. With the right pad, you can have very, very good performance, very, very low weight, low dust. It is expensive. So it's an expense that if you're doing a track day event, it can be very easy to overheat those brakes, and they wear out by reducing weight. And what that's actually doing is taking carbon that's inside that brake rotor, and at elevated temperature, it will turn back into carbon dioxide. So essentially what it's doing is becoming more porous and losing weight. And so that's why there's a weight specification on a disc like that. And it's also why, because there's no actual wear happening, it's very hard to tell if they have gone over temperature range. So it's a very common place now to replace a carbon ceramic disc with its high cost with an iron brake system when you're doing high performance track driving, racing, because it gives you the ability to put in an iron lower cost solution that has very good braking performance, and be able to save your expensive carbon ceramic rotors for the street, for resale of the vehicle, any of those applications. And we just did a full system replacement with TPC Racing with Tom Chan, where we replaced the entire PCCB system, which is a carbon ceramic with the calipers, with our PFC track day system that has an iron rotor and carbon metallic brake pads, calipers front and rear, and our two-piece racing brake assemblies. So in developing a brake system for such a high level of car already, the electronics, the ABS systems, what they're looking at is data for torque, data for brake pressure. So they're expecting certain results when you apply the brake pedal. So what you have to keep in mind is to stay within that hydraulic sizing and that kind of frictional range that it's expecting, and not overstep the bounds too far. You can make minor changes here and there to help improve balance. You can maybe you add rear braking power, maybe you add more front braking power, depending on how the vehicle was set up from the factory. There's always a little room for a certain improvement for a specific scenario, such as racing on a track. Because overall, the engineers have developed that car to handle a whole multitude of scenarios, from high performance driving to driving in the snow, to driving, well, to your grandmother driving the car. It can be anyone doing this, so there's a little bit bigger range for what the vehicle needs to do from the factory, versus when you're saying, hey, I'm going to do a track day high performance driving event, I'm putting stickier tires on, which means you can change up the brake characteristics a little bit and still the factory system will be fine. But yeah, if you overstep the bounds and do too much, it's why if you say took a 20 piston caliper that had many, many more pistons and a lot more hydraulic area in the front, you're not going to be able to use all of that torque it's generating. You'll just lock the brakes up, ABS will engage, and you won't have a very good stopping car. Likewise, if you put too much at the back axle, the ABS will engage. It'll want to keep the rear end from locking. But you can stay within a window and design around the parameters. Obviously, we want to keep weight down. Obviously, the iron conversion rotors are heavier than a carbon ceramic, but not so negatively so that you can't still see high performance from the vehicle. So today's high performance vehicles are very sophisticated. Braking systems are using a lot of electronics to monitor what's going on. But the reality is that the heart of the system, the hydraulic braking system, really isn't any different than a 99 Corolla or a 1950s vehicle with disc brake technology. The basis of the system has stayed the same. So for a manufacturer, our parameters haven't changed a whole lot. Yeah, it changes based on the vehicle needs. If you have a very heavy vehicle versus a very light vehicle, racing vehicles, different applications, it all comes down to sizing the components best to fit that application, whether it's torque output or weight reduction, durability. So those are kind of the key aspects we always take into account. Now, one of the areas where vehicles are getting more sophisticated with recent use is what's called brake-by-wire, where you're no longer connecting the brake pedal directly to the hydraulic system. The brake pedal is now more of an electronic sensor, which gives a signal to another hydraulic booster device to apply the brake pressure to the calipers. So vehicle systems are starting to get into that now, especially with electric, with hybrid, blending those two technologies together. Those bring more changes for us than anything as that comes about more and more. It's still not mainstream enough that it affects us too much in racing, but it is something that is coming where we're having to blend that performance of a hybrid performance and regen braking with a hydraulic system performance. So the computers are what become more and more important to do control systems on brake hydraulics that were never done before. It's no longer just a push the brake pedal and apply the load to the wheel end. The computers jump in and do a lot more, even to the tune of helping control the car to make it faster. Torque vectoring can make a car faster through cornering. So you can brake a rear wheel and actually allow the car to rotate through a corner faster than it could if you didn't. So a lot of new devices that are coming about that are becoming more mainstream that do some changes for us, but still the key heart of the components with brake rotors, pads, hydraulic systems still remain mostly the same. Yeah, so with Tom's car, what we did is to replace the whole PCCB system, factory brake system came off, we put on a PFC design system. So 3 key areas there that we've changed out. We changed out the brake calipers and pads and the brake discs. So those are kind of the 3 key areas of a braking system. So with the brake disc, it's to replace the PCCB so that you don't have to potentially damage your expensive PCCB set on a track event. Plus, again, with the frictional characteristics that you're looking for on more of a racing or track event, the iron is a little easier to have a better brake pad to generate the torque, the stopping power, the brake feel that you want than the PCCB. You do take a hit on the weight. The iron is heavier. Some of that's made up with the discs having a smaller swept area. So physically the discs are smaller than the PCCB. That helps reduce some of the rotating mass and the weight. But also what we do is with a 2-piece assembly that has both axial float and radial float, it allows that disc to move to account for any manufacturing tolerances of where the disc doesn't run perfectly down the center of the caliper. And when it does that, it can create drag. So if a disc is free to move, it reduces drag, produces a slightly better braking system. But also importantly for the iron, because of thermal mechanical stress when it gets hot, you need the iron to be able to kind of grow freely with temperature. So that's why you want a floating disc on a racing or track day type setup, is so that iron can grow and reduce cracks or problems that can happen with iron. So we've done a lot with our discs, from metallurgy to the geometry of the tabs, the geometry of the disc, and the hat combination to help ensure that that iron can grow as freely as possible when you see serious heavy braking. The brake pads that we develop with our carbon metallic technology are very low compressibility pads. When we talk about brake pads on the street, you can have a little bit of compressibility, which actually helps make it quiet. But what that ultimately means is some of your braking force is being wasted on compressing materials. So if you want all that brake energy to go into the brake disc, you need to have a very hard, low compressibility brake pad. But that does bring some low speed noise, some squeals, some grinds, things that aren't a problem with a racing brake system or aren't a problem with that system at all, but they just add a little extra noise over a street system. Cost is a big factor for designers and for manufacturers. So it's like I noticed, it's like probably a lot of people don't know that the upright for the factory 991 GT3 street car is also identical to the upright on the GT3 Cup car. Just a couple different machining differences that allow them to use the same casting. Yeah.
Gotcha. Yeah.
So they just a couple different machining differences. Now they can take that one cast piece and move it to many different options. A lot of the vehicles out now are still running basically the same uprights that were designed for the 996.
Interesting.
So like Caymans, Boxsters, entry-level cars, they're running that same. Because ultimately there's nothing wrong with that design, and especially when dealing with casting parts, forging parts, there's a lot of investment in tooling to get that part made, and the more parts you can make and the more you can use it once it's been made, it becomes more effective. Part of any engineering design exercise is you've got to pick and choose your battles in a way. With the engineering background I have, in my position, it's the same. You can't always say, well, I want to design the greatest thing ever, because it's going to be very, very expensive and it's going to be very hard to make. And so it's just, you can't make money doing that. So as an engineer, you both have to understand the mechanics and performance that you need to get, but then also work within the bounds of manufacturing and production of a component that is going to be sold and people need to buy. And so not everybody can afford to have the absolute engineered to the utmost degree. So getting back to the brake systems, it's like the brake systems on the Porsche with your PCCBs or your iron, the calipers on the front axle are the same calipers front and rear, different paint, but hydraulically the same. It's to cover economies of scale. You can produce more parts with different machining. Now they are produced specifically for a PCB setup, different machining cuts, different mounting points versus the iron. It also runs a different brake pad. So one of the things they're doing with the PCCB is it's got a very tall brake pad, and that's to manage heat again as well. So again, why swap out a PCCB system? We talk about heat, damage, resale value, but ultimately they've made that PCCB bigger because you need the pad to be bigger to be able to absorb heat, because the carbon ceramic doesn't absorb heat like an iron does. An iron brake system can absorb heat and stay pretty stable, versus the PCCB doesn't. But one of the things we've changed out on our system that's a difference, it's like, well, why can't you just take an iron rotor and put it, with the PCCB caliper? And in fact, that's done. We have iron rotors to do that. We have a conversion set that can swap out just the rotor if you don't want to go to the caliper. So there really are kind of stages, and we see it, what we do, as a stage effect of what you need to do. The foundation of a really good braking system is your brake pads and your brake fluid. That's kind of the starting point. Anybody can utilize that, from the street car to performance driving. And as you start to get into performance driving more, dedicated track events, you'll find, okay, my stock brake rotor, if it's a one-piece iron, that iron can't float as well. It's cross-drilled. It might crack a little as you put more heat into it. So it's like, okay, now I can upgrade to a rotor that has a better friction ring, that has more stable friction, which allows me to also go to a more aggressive brake pad. And then it's like, only after that, that if you push the bounds of that and finding, okay, my stock system is still not able to handle the heat. The brake pad thickness is the next thing you can address. So when talking about some of the things you have to do for a street brake system, there is a whole myriad of design into the front wheel end, suspension, brakes, wheels, geometry of the suspension that has to be dealt with. So you can't always make the brake system have an ultra wide brake pad, which is great for heat, but not great for packaging. So one of the things that probably the most time spent on the brake kit was making sure that the brake calipers that we have designed to fit the Porsche applications would be able to clear the factory wheel. So being able to model and trim a little here, trim a little there, get a couple extra wheel models to see, okay, how can we make this work with a factory wheel? If it's an aftermarket wheel, that's easy. They add a lot more brake clearance in because it's something that you're going for. but a factory wheel. That all plays into the effect of why the factory brake system can't handle actual racing or heavy-duty braking on a track type scenario. I don't know if anyone knows or has seen NASCAR racing brakes. They've been pigeonholed into a 15-inch wheel for a long time. So when you need to dissipate heat, the only place they could go with the brake system was wider. So NASCAR brakes are some of the widest brakes, where your brake pads could be 30 to 35 millimeters thick. The brake rotor itself is 40 to 42 millimeters thick, because you need to dissipate heat energy, and you don't want that heat energy to go into the caliper. Unfortunately, an aluminum racing brake caliper, aluminum in general, makes a very, very excellent heat sink. So the more heat you have near it, the hotter it gets, the hotter your brake fluid gets. If you burn up your seals, your caliper will either leak or the pistons won't retract, causing drag and more heat, which will just worsen the problem. So what we do with our track day brake packages we've done for the Porsche application is to offer a much thicker brake pad to go with our caliper. So that means that our caliper can be a little lighter, but it does have to go wider, so that it means it will not fit every single wheel out there. Sometimes it won't even clear a factory wheel. We've done a lot of work to make it fit the 991 GT car wheels, which have a lot more clearance. But that's kind of the heart of the braking system, and the caliper really revolves around the brake pad. If you can go to a thicker brake pad, you have so much more mass to be able to dissipate heat without it getting into the caliper.
Break
Oh.
into deer to just shake your head. Do that. Do
Yeah.
exactly that. Just do that.
I was thinking of a
They're
couple
just fine.
things, and it's like, oof.
Yeah, and there's.
We see things a lot. You find things on the internet, you pull up something that someone's done, someone said. It's like misconceptions about brakes. Probably the number one biggest misconception, the thing that we kind of shake our head at, is, I guess, the misunderstanding that the brakes stop the car. Well, that sounds like a very bold statement to say. It's like the brakes don't stop the car. And it's because ultimately, it's the tires that stop the car. So number one is, like, if you don't have a very good tire, you could have the best brake system in the world, but it's just going to lock that tire up. So it's part of why everything, when upgrading or modifying a vehicle, you need to look at a complete package. It's not just, let me throw the biggest brake system on there I can fit into a wheel. But it's like, okay, what is this doing when I put this on? Why am I doing it? Again, like I talked about, the brake system's biggest role is to manage thermal. You're trying to convert mechanical energy from driving 150 miles an hour on a racetrack down to 20 miles an hour. It's a lot of energy. That energy gets converted to heat. So the brake system's real role is to convert that mechanical energy into heat energy, which then can be dissipated in the environment. So how do you handle that heat? And that's why we develop high-performance braking systems that can handle that heat energy. But yeah, so that's kind of one of the big first ones. We're like, okay, the tires are doing the work of slowing and stopping the vehicle. Another one I was thinking about, and why I was like, put my hands to the face, is some of the things you see, scalloped brake rotors, things that are done very aggressively, that are more of a, they're great, they're marketing. It's like, we look at this fancy looking brake rotor, but ultimately it's like not doing that much for you, to where it's like, oh boy, it's like the key to any good braking system is having a very stable caliper, because you want everything to apply loads into the brake discs with very good equal pressure. If you have a very flexy caliper that twists and bends and is just ultra light, those pistons distort. The heat energy that goes into the brake disc is not very even, and what that means is that cast iron rotor will warp and distort and move in ways that will produce cracks, and you'll have a very poor performing brake rotor. So it's like, our concept at PFC has always been to have a very durable, very high stiffness brake caliper, because that allows you to have a much lighter brake rotor. You can have a lighter iron brake rotor because the thermal energy going into it is much more stable. You don't have to worry about it distorting and cracking and doing things if you were to put a very flexy brake caliper on it. Filling up a wheel is a big thing now. With the wheel diameters that have gotten bigger and bigger, 20, 21 inch, 22 inch wheels, I agree, it does look physically better to have a brake system that just fills the entire wheel. But that means a very, very large brake rotor. Carbon ceramic, you don't have the weight penalty. But an iron rotor, we're talking, there's a lot of cars out now that have 40, 45 pound brake rotors on the front axle, 420 millimeter iron rotors. It's just big and heavy. And that's not great. Does it matter so much when you're driving to the store to get beer and pizza? No. Does it matter for 90% of the drivers out there doing a track day event? Probably not. There are a lot of things that are done in racing, obviously, to gain minute advantages. In braking on a racetrack, most of your passing occurs in a brake zone. So advantages become huge there, or advantages of a few tenths of a second over a lap. IndyCar racing, which we do all the brakes for the IndyCar series, they're trying at the Indy 500 to eke out maybe 241.2 miles an hour instead of 241.1. So at that speed, every little thing becomes very, very important, from the weight of the brake rotor to the balance of the brake rotor to drag in the system. So it's like, that's ultimate level of brake performance and technology and things that need to be done. But yeah, it's like, what do you need to do on a street car? But I get it. There is also a lot of personalization and style that it's like, while it's not necessary, it doesn't hurt having, let's say, an oversized brake system. Where it does hurt, though, is, however, if you try to engineer your own system and think, I'm going to take these awesome big brakes from the rear or from the front of this Porsche, and I'm going to put them on all four corners of my cars just because it's big. If you don't have a basic understanding of the hydraulic systems, the mechanics, to understand what's going on, you really shouldn't be even attempting that. Even if it's on a Porsche to another Porsche, you've got to be careful with that, where you can't just say, I'm going to take the front caliper, put it on the rear because it will physically bolt up to it. Just because it physically bolts on doesn't mean it will work properly. Now, that's not to say you can't take, a brake caliper from one make wouldn't fit or work for another. Because hydraulic sizing is pretty simple. It's hydraulics, piston bore sizes, master cylinder sizes. Most cars are pretty similar. Sports cars, 3,200 to 3,800 pounds. It's either front engine or mid-engine or rear engine in the matter of Porsche. But physics and weight transfer is all pretty similar, and that's why you'll see a 6-piston front caliper, 4-piston rear. You need smaller brakes on the back. You transfer weight to the front axle, and as stickier tires come with racing, you actually transfer more weight to the front axle. So it's where a true racing brake will need even more braking in the front, except in the case of high downforce cars. Like IndyCar uses the same caliper front and rear because it's designed that way, and the vehicle is set up to where it has so much downforce that you have weight on the rear axle as well as the front axle.